In this video, I want to do the Chapter 10 portion of the test review. And this is the first question dealing with Chapter 10. That was the acid-base reaction, or acid-base chapter. And it's wanting us to complete this, what's hydrolysis reaction, where this ion is going to react with water. And so there'll be a proton transfer occurring here. Now, in this particular example, it's go ahead and tell us that we want it to act as an acid. And we do see that with the hydrogens on the front end of the formula. That does indicate that it can act as an acid. But also keep in mind that if you have an anion in solution, they can react as a base. So there are a few of these compounds that can go both ways. And it's these hydrogen or dihydrogen ions, like dihydrogen phosphate here. Okay, so let's just get this out of the way. It said it's going to act as an acid. That means that the water is going to act as the base here. Well, remember what that means. That means that there's going to be a proton transfer that occurs in this direction in the reaction. And it's one of these. So it removes a hydrogen and it removes a positive charge. Well, what does that look like? Well, one thing, it looks like that. I'll talk about that in just a second. Minus one hydrogen. Okay. And if I remove a positive charge from the dihydrogen phosphate, then that means that you're going to have a -2 charge now. And that positive charge is going to show up on the water molecule in the form of the hydronium ion. So all of the strong acids, you have the halogen group, so HCl, hydrobromic acid, and hydroiodic acid. You have a couple of other common acids like nitric acid and sulfuric. And then the last one for us is perchloric acid. Yep, so 6 strong acids. Any other acid is going to be a weak acid. So if it's a weak acid, we use this double-headed arrow to imply that it's a weak electrolyte. Okay, finishing up this particular question, we also want to know, we want to label the conjugate acid and the conjugate base. Well, the way this works is that once the acid gets rid of that proton, then it turns into something we refer to as a conjugate base. And then once the base receives or accepts the proton, it turns into what we call the conjugate acid. Now, problem number 12, that is a titration calculation, all right? And so there's a couple things you got to worry about here. One, you're going to be looking at the balanced equation you got to figure out. So let's just go ahead and get that out of the way. Remember, there's a handful of those reactions of acids. This is a neutralization reaction. That's one of them. The other one is a production of CO2 when an acid reacts with a carbonate salt. And the third one is the production of hydrogen gas when the acid reacts with a metal. Okay. So here's a neutralization reaction. It doesn't matter which one you write down first. 2 aqueous solutions coming together. And the what we say is that the salt and water forms. Okay. So the water formation, that's really the main characteristic of that neutralization reaction. You have something that started out as an acid, something else that started out as a base, right? The pH is something other than 7, and then you wind up with water, which has a pH of 7. The salt portion, well, that would be really associated with the spectator ions. So let's just make a few little. So I just copied that onto a blank sheet because I want to make some marks here, and I don't want to use up all the space on that previous page. Okay, so the salt formula. Let's talk about it. Okay. Now the water formed from the formation. Actually, let's just do this. Now, what's characteristic of an acid? Right, it kicks off a proton. Which portion of this salt is the base? Well, it's hydroxide. Right, the classic setup. And these two are the things that are coming together to form water. Now the other components, what are essentially the spectator ions here, they are the ones that are going to come together to form the salt formula. But you have to get that salt formula correct here, otherwise balancing this equation can really cause you some headaches. As it turns out, the magnesium has a +2 charge and the phosphate has a -3 charge. On an acid, You can always determine the negative charge on the anion based on the number of protons that you have there. So notice the 3 and the 3 match up. And the magnesium, it's in the second family on the periodic table. It always takes on a +2 charge. So if I want to get the proper salt formula here, notice what that's going to look like. I need, for every, I can't bring them in a 1-to-1 ratio. I would have, the charges would not be balanced. I have to have some, combination, a ratio to where the charges cancel out. And that's achieved by having 3 magnesiums and 2 phosphates. Right? If I add it up, that's a +6. Add these up, -6. There's where I'm canceling out. Notice 3, 3, 2, 2. And then something we talked about, it was a chapter 15 video, or lab 15 video. Right? We can say that the charge on one tells me how much of the other that I need. So that works out well for this particular example. Okay, so that's all the sort of marking up I wanted to do. Let's get back to the titration reaction now. And I'm not exactly ready for the titration calculation because I first have to balance this equation. My recommendation for balancing these reactions, I would start with the salt formula. You can really start anywhere you want to, but sometimes starting certain places speeds these things up. If I start with the salt formula, one thing to notice, if I look at the ratios or the complexity of the molecules, this one's the most complicated one. That's a pretty good place to start when you're trying to balance these things out. It just really speeds up the process. For example, I got 3 magnesiums. I need 3 in front there. I have 2 phosphates, right? If there's parentheses around the phosphate, then whatever's outside the parentheses applied to that that's inside the parentheses, so 2. 1 shown here, so I need 2. And then notice what happens here. I have a total of 6 hydrogens. I think I can put it up here. Let's take a look. So 6 hydrogens plus 6 hydroxides, 2 times 3. Well, something we just saw a second ago, right? This forms water. You got 6 water molecules. That's the net ionic equation, by the way, for these reactions. Now we're balanced. Now we can do the calculation. What I like to do with the calculation is sort of take this information here and then place it with the appropriate reactants. So I have a 50 milliliter sample of the phosphoric acid. It's titrated with a known concentration of the base, and it took 27.5 milliliters of the base to reach neutralization, or to reach the endpoint. And I want to know, right, I want to know the concentration of the acid here. And something we talked about before, right, we always, where to start, where to finish. Well, you want to finish there. That means you start where the data is and you go toward where there's less data. And what I always tell my like Gen Chem 1 students, when in doubt, calculate moles first. The reason why I say that is because, right, these coefficients here and here, they are molar coefficients. So if I'm going from this compound to that compound, the only connection between those two is the unit moles. So how do I get moles out of this? Well, it's embedded within that molarity formula. Right, there it is. I just need to solve this formula for molarity, or for the number of moles, I should say. And one way to do this is the equation triangle. If I want to calculate moles, then imagine covering that up and then reading this. So moles equals concentration times liter. So that's going to be my first step here. Oop. And let's just start doing that. Now, actually, just for the sake of sort of symmetry and a typical layout, I'm actually going to write down the volume first here. Notice all of these are going to be in milliliters. You need to convert them to liters. And what you do is you divide by 1,000 in both of these cases here. So you're moving the decimal over 3 places to the left. Now the reason why I did that, why I wrote down the volume first, because, well, that's a lot of times what you do, just to make it look like a dimensional analysis problem. That's what I'm shooting for. Because what I want to do is I don't want to just put a capital M there. I want to break apart that M. You know, what does that mean in there? A concentration of 0.125 molar means that there are that number of moles in 1 liter of the sample. This is a conversion factor between the units of volume and then the units of amount in terms of moles. And just like any other dimensional analysis problem, you know, the unit that you're starting with, it's that portion of the conversion factor that is going to go on the bottom, and then the other portion is going to go up top. So yes, the formula is correct based on equation triangle or algebra, but it also works in the context of dimensional analysis. Because if I did this math, I would have the liters canceled out. Moles of what? Moles of my base. And so moles of my base. What I mentioned this, well, it's 3-to-2 mole ratio between the base and the acid. That is going to be used in my next step. Which one goes in the bottom? Well, it's the one that I have right here. It's moles of the base. So the 3 moles, of the magnesium hydroxide is going to go there, and the 2 moles of the phosphoric acid go there. And actually at this point, if I did the math, you know, moles cancel out, moles of magnesium hydroxide cancel out, I'm left with moles of my acid. Well, in the final step, if I want to calculate molarity, what's molarity? Moles divided by liters. So moles divided by liters. And then just a reminder of the math, right? Any numerical value on top, you'll multiply by. Anything on the bottom, you will divide by. And if you crank this through, what you get is .0557 molar. And I am using 3 significant figures here because, well, all of my data have 3 significant figures. Remember, when you do like this is really an exact relationship here. There's exactly 2 moles for every 3 moles, so there is no uncertainty. We say that with exact relationships or exact numbers, there's an infinite amount of significant figures for what it's worth. But you do round this one to 3 sig figs. And really the last topic for, chapter 10 here are these acid-base reactions. You'll have these formulas in front of you when you do these calculations. And I think I'll do this one first. It's going to be the easiest. Like, for example, when you have just a 1 in front of the value, you don't even really have to grab a calculator if you don't want to on this one. There are ways to do the calculations without a calculator here. Let me show you how we do that. So the first off, let's recognize the fact that pH is related directly to the hydronium ion concentration. When that value is 1 formula that you see in the textbook looks like this. If the hydronium concentration has that 1 in front, then whatever the exponent is actually the pH of this solution. So it's 8.0. Remember your sig figs, these weird sig figs when you're dealing with pH calculations. The number of digits, the number of decimals on the pH measurement corresponds to the number of numbers in your hydronium ion concentration. And then if you're wanting to go from this to that, we're going to use this equation. It's that it was a self-ionization of water, the Kw value that we saw in chapter 10. So we say that the concentration and the concentration of hydronium times the concentration of hydroxide, that product is always constant in an aqueous solution, and it's equal to 10 to the minus 14. Well, if the pH or the hydronium is 10 to the minus 8, to go from minus 8 to minus 14, this has to be 10 to the minus 6. So when you're multiplying exponents like that, or I should say, when you're multiplying numbers in scientific notation here, essentially what you're doing is you're adding the exponents. So minus 8 plus minus 6 gives you minus 14. And so that's actually the concentration of hydroxide. Now, in this top example, we won't be able to do that. Okay, we'll actually have to do it the hard way. And speaking of hard ways, going back from pH to hydronium ion concentration. Okay, so the typical set of formulas that you see here between pH and hydronium would look something like this, where we would say hydronium is equal to the, well, sometimes you hear well, I'll just write it out. The antilog of the minus pH, or another way to express that is this formula, 10 raised to the minus pH. If you look at the log button on your calculator, the second function of that log button, the log button, will look something like this. Usually 10 raised to the minus x, or 10 raised to the x is often what you'll see. But usually I just plug in 10 and then raise it to the minus pH value. So this would look, using this formula, look something like that. And when you hit equal, then what you get is this number. And you can also do this by hitting the second function and then the log button. There we go. And that's the concentration there. Now going from hydronium to hydroxide, we're still going to use this formula, but we can't just do this simple like addition math of the exponents. Instead, what I have to do is I have to solve for hydroxide. Let's do that. So if we take this formula here, what we can do, if we divide both sides by hydronium concentration, I get this formula. Plug in that value. And the final answer here is 1.3 times 10 to the minus 9. And you can always double check your work here. If you multiply those two numbers together, then, well, it should give you the 10 to the minus 14 value, and it will. Last word on this, sig figs, just like here. I said the number of digits, the number of decimal places on the pH value indicates how many numbers you use in your hydronium and hydroxide values. pH 5, that is acidic. pH 8 is basic. Okay, thanks.